So we will now spend the next 1 or 2 weeks just going over the introductory material to the theory of computation. That's mostly because the audience here is quite diverse, which is actually excellent. That's how it should be for this subject. So just to motivate the Blackboard talks that we will have, let me start with the following science-themed thought experiment. So imagine you want to colonize Mars by deploying a fleet of machines that will progressively transform the planet's atmosphere. And suppose you are rich. Well, once you do the math for all the costs, you realize they will quickly skyrocket, and you might not be rich enough to cover specifically the transportation costs of such a process, because as the old machines will go out of order, there will be the need to continuously ship replacements. But suppose you're also creative and you realize that if you design the machines to be built from materials that are abundant on Mars, then if you manage to create such machines that can self-replicate, all that suffices is for you to ship an initial generation of machines, and those will contribute to the terraforming process, and just before going out of order, they would create an exact copy of itself that will continue in the terraforming process and will also self-replicate. Now, this is quite an interesting solution, but the key question is it even possible to design such machines? If we disregard von Neumann's contribution, the only examples of machines that humans have built are machines that can only build machines that are simpler than themselves. Even the example of a 3D printer can print parts of a 3D printer, but is unable to build a fully functional 3D printer that would be ready to start printing as soon as it's finished. And so there seems really to be this paradox of the following kind. If there is a machine A that is supposed to build a machine B, it needs the complete information about B, as well as further mechanisms that are able to understand that description and actually build the machine. So it inherently seems that A has to be more complex than B. But on the other hand, nature did seem to find a solution, as multiple or diverse range of organisms is able to self-replicate and even produce offsprings that are more complex than themselves. So maybe after reading von Neumann, or maybe after looking at biology, we decide not to despair. And following von Neumann's conceptual distinction between the actual machine, the constructor, and the tape, we can actually split the problem in two. One is to design the actual constructor, which is complicated enough to understand a rich range of descriptions on its tape, and according to those descriptions, physically manipulate parts around itself to build new machines. And the actual tape, or the blueprint, or the program, which specifies not only the function in the machine's terraforming process, but also at some point the self-replication process, which essentially has to say, okay, manipulate this part around yourself to build this type of machine, but at some point it has to also say, and now copy the contents of this whole tape or of this whole blueprint, referring to itself. So in some sense, we can for now postpone the physical part of the problem, that is the design of the constructor, and just focus on designing programs that are somehow deeply self-referential and can produce their own description. So that also does not seem a priori super clear that it is possible, but it will turn out that the theory of computation gives us such an answer. And in fact, this is something we will get to in 2 weeks, to the Kleen's recursion theorems, which are some of the deepest results related to this self-reference. So for now, we will just focus on some of the most fundamental definitions, which concerns with the abstract mathematical definition of what a program is, which was due to Turing. There was actually multiple different attempts to formalize what a computational process is, coming from Gödel, from Church, and from Turing. But all of these turned out to be equivalent, which really shows that they are pointing towards something profound, and led to the Church-Turing thesis that actually an algorithm or a computational process is anything that can be implemented by a Turing machine. So let's start. So actually, let's start with a terminological window. So in some contexts, we will call finite sets alphabets, specifically in contexts where we will consider finite sequences of elements from such a set. So let sigma be a finite set. We will call it the alphabet. And by sigma star, this is the clean star, we will denote the set of all finite sequences over sigma. Including the empty sequence. That we will denote by epsilon. Great, the mic is still on. So or let's say, okay, a Turing machine often abbreviated TM is a triple T equals Q sigma delta, where can you read the writing well? Okay. Where Q is a finite set of states including two special symbols. Q0, the initial state, and Q halt, the halting state. sigma is the input alphabet. And this square cap will denote the blank symbol. Which is not included in sigma. By sigma prime, which is the union of sigma and the blank symbol, we will denote the tape alphabet. So input alphabet is a finite set of states excluding the blank symbol, and once we add it in, we have the tape alphabet. And lastly, delta is a function which, given a state and a tape symbol, determines the next state, the next tape symbol, and one of the three following symbols that we will explain in just a second. But you can for now interpret them as left, middle, and right. Is the transition function. So if you spot any mistake, by the way, let me know at any moment, please. Great. So as such, a Turing machine is it's a static object, it's a triple, but it defines the following computational process. So each Turing machine defines the following computational which operates on a B-infinite tape of symbols. Or of cells. In the following way. So, given the input which is a sequence of non-blank symbols, the process is initiated with the tape containing, so let's assume that X is just the sequence of symbols S0, S1 to Sn minus 1. So maybe another terminology window is that for us, natural numbers will start with 0. It has multiple reasons. So the tape is initialized by indefinitely writing the blank symbol to the left, then writing exactly the input sequence, and then indefinitely writing the blank symbol to the right. And the process will consist also of the so-called head, which is at the current time step has access to one particular cell of this B-infinite tape. So it's initiated with the tape and with the head reading the symbol S0. And we will consider the head to be in the initial state Q0. And being in the state Q0. And now this computational process will change the states and the tape content based on the transition function delta in the following way. So suppose the current state is Q, so a state from the set of states, and the head currently reads the symbol S, which can be blank, and we have the transition telling us that if we are in the state Q and reading the symbol S, then the new state is Q prime, the new tape symbol is S prime, and the movement is A. So then the head changes its state to Q prime. It erases the current symbol S. And writes S prime instead. And lastly, based on A, the head changes its position relative to its current one. And finally, it moves left if A is equal to L, stays at the current location if A equals to S, like stay, or moves right if A equals R. So initially we had the input S0, S1, Sn minus 1, blank symbols to the left and right, and we had Q0. Now imagine that delta of Q0, S0 is Q5, S prime and L. Then In the next time step, the computational system will change its state to Q5. It's gonna erase the symbol S0 and write S prime instead. And the head is going to move left. So now it will currently be reading the blank symbol. So hopefully that's clear. And so what can happen? So this iteration just keeps on progressing until if at some point the head enters the state, the halting state, we say the computational process terminates. And we write TX down arrow. And at this point, we would like to define some output of the computation. So if there is a single contiguous sequence of non-blank symbols on the tape, some y from sigma star, we say this is the output. Otherwise, if there are multiple segments split by the blank symbols, we just define the output to be the empty sequence. However, not every computational process needs to terminate on every input. So the second option that can happen is that the iteration just keeps on indefinitely progressing, and in such a case we say that the computation diverges on the given input. So otherwise, we say the computational process diverges on X, and we write TX up arrow. So there's two objects that are fundamentally different. There's the Turing machine itself, which is not the computational process, but it defines a computational process that we have just described. So let's just capture it in a definition. So let T be a Turing machine Then it defines a partial function phi t from the set of non-blank sequences to itself. Since it's partial, let's write this. Which maps each input x to the corresponding output y, as we have defined earlier, if the computational process halts on x, and otherwise phi of t x is undefined. So we say that a function phi from sigma star to itself, potentially a partial function, is a partial computable function if there exists a Turing machine T. So let's start with Q sigma delta such that phi is equal to phi t. And in such a case, we will also say that t implements phi. So moreover, if the domain of phi is everything, we say that phi is a total computable function. So let's finish this section with the Church-Turing thesis. An algorithm is exactly such a computational process that can be implemented by some Turing machine. Be implemented So sound is still going, that's good. So there's uncountably many functions between all the finite sequences, all the sequences of a finite set to itself. And let's say Turing machines carve out a special subspace of these functions that can be implemented by one. Enter's Turing thesis is essentially a definition of what an algorithm is. So the intuition you should have in mind is whenever you write a program in your favorite programming language, you're essentially defining a particular Turing machine. And the key observation is that really you could convert every program that you write into a particular Turing machine, though it would be pretty painstaking because this is a very low-level programming, let's say. But this will be the main point of the exercises, is to really see that any kind of basic operations that you can do in a programming language, you can kind of define via Turing machines. And we will develop on this intuition next time. And as soon as you kind of execute your program on a particular input, you kind of implement this computational process that will give you a specific output. And if you're unlucky and you define your program not well, it might never stop at the computation. So it will be useful for our purposes to view the partial computational functions as maps between natural numbers. So we will somehow have to form a bijection between the natural numbers and the set sigma star, but not just any bijection. It has to be a bijection that is in itself implementable by a Turing machine, so that composing two computable functions, we get a computable function. So one more piece of terminology. We call a bijection F from N to some set S, an enumeration of S. So for now, assume S is a subset of some sigma star for some sigma. We say that F is an effective enumeration of S if F is a total computable function. So our first step will be to show that there exists an effective enumeration of the full set sigma star for a fixed sigma finite set. So effectively enumerating sigma. And this could form some kind of analog of Gödel's incompleteness theorems, where we will essentially encode more and more complicated objects into natural numbers, starting with finite sequences. And next time, spoiler alert, we will show that the set of Turing machines themselves can be effectively enumerated, which will be a crucial step towards defining a universal Turing machine that can perform any computation there exists. So there's multiple ways to enumerate sigma star. I will show one based on the maximal lexicographical ordering. I think it's going to be nothing new. So we fix the set sigma. And suppose it has n symbols. So let's choose an arbitrary order on sigma, for instance, that S0 is less than S1, so a linear order, Sn minus 1. So this induces the following linear order on sigma star. Good. So for xy from sigma star, so we will denote the linear order by the curly inequality sign. So x is less than y if either the length of x is strictly less than the length of y. So now we have an abundance of different orders. So this one is just the natural order on integers. So maybe we can continue our terminological window. So for x from sigma star, we define its length to just be n, and we define the length of the empty sequence to be 0. So hopefully that's clear. Or if their length is equal, so then x is less than y if x is strictly less than y in the lexicographical order, and yet another order induced by this order. So this is the natural way you would order words in a dictionary. Imagine they all have the same length. You first search by the first letter, and if you have a match, then you search by the second letter, and so on. So on an example, suppose we have S0, S3, S1, and S0, and S0, S0, S6. So this is the second case. So we start by comparing the first symbols, and since they're equal, we move to the second symbols, and here we see that S0 is less than S3. So this induces this order between the two sequences. Hopefully this is clear. And this allows us to list all elements of sigma star from the smallest one so which one is the smallest one? It's the empty set, perfect. Followed by all the sequences of length 1, so S1, S2, all the way to Sn minus 1, and then by all sequences of length 2, and we can define a function beta from n to sigma star, which sends n to the nth smallest element of sigma star with respect to the order we just defined. And it is not hard to make the following observation. So this is an I, that beta and beta inverse are bijections, which are both total computable functions. Indeed, it's not so hard to define a program that on an input n will start listing all the sequences from the shortest one and keep a counter until it reaches the nth sequence, and it's going to output it. And it's also not so hard to define a program that will do the inverse. Good, sound is still on. So you might be a bit displeased that we talk about beta being a total computable function, even though it's not a self-map. But here we can just, or natural numbers are not a set of finite sequences, but here you can just fix your favorite base k and represent all natural numbers with respect to that base, and they literally just, you can represent natural numbers as sequences in that base. And if you want it to be somehow equivalent to sigma star, you can choose k to be exactly the number of symbols that sigma has. And in the last few minutes we have, let's introduce one more definition. So we have already discussed what does it mean for a function that maps a finite set of sequences into itself to be computable, or what it means for an enumeration to be computable. So there is one last object that you will classically encounter in the literature as being considered computable, and that's the subsets of natural numbers. So let S be a subset of n. We say that S is decidable or recursive if the function S, which I either outputs a 0 if S is not an element of S, and outputs a 1 if S is an element of S, if the characteristic function of S is a total computable function. And further, we say that S is recursively enumerable if there exists a function f so a partial function f such that f of s is 1 if and only if S is an element of S, and f of S is not 1 or is undefined if S is not an element of S. So clearly, being recursive or decidable is a stronger property than to be recursively enumerable. In the next exercise sheets, you will have a chance to get used to this notion and see or prove that it is equivalent to the existence of a Turing machine, which from an empty input starts listing all the elements of S. So whenever we are interested whether a particular element is a part of S, we have a guarantee that we will for sure know at some point, but for an element that is not a part of S, we will never have that guarantee. We will never know whether we should just wait for the computation longer or whether it will never really output that symbol. And since the terminology is pretty rich, let's summarize this in the following table. So this will be the let's say the computable objects, and they will either be implemented by a Turing machine or implemented by a Turing machine that always halts. And the objects we have considered are either partial functions or enumerations. Okay, this time. So or just a subset of the natural numbers. So in this case, we say that f is partial computable and total computable. Here, we don't really have a notion to describe this, but here we say it's effective because we already assume this function is defined everywhere because it's a bijection. And here we say that it's recursively enumerable enumerable, or just recursive or decidable. Are there any questions? Then I think that's it for today.